Hey guys, this video will be covering the concept known as independence of motion in two dimensions. So, if you think back to our riverboat lesson where we worked with a lot of riverboat problems, and when we were doing the calculations, I told you guys to pretty much keep the x and the y dimensions separate. Why do we do that? I could have been just arbitrarily telling you guys just to separate those two, but there is a reason why we do that, and in this lesson we're going to cover the reasons why. Before we get into that, first things first, let's start with a question here. You're holding two objects from the same height. At the same time, you throw both objects horizontally with different speeds. Which will hit the ground first? You don't have to answer this now. We're going to go back to this and answer this by the end. So then, what is this idea of independence of motion in the two dimensions? Well, there is this idea that the motion of an object in the y direction is independent of the motion in the x direction. This also holds true in 3D motion and higher. So essentially, in other words, whatever happens in one dimension should not affect what happens in the other dimension. And this holds true in higher dimensions, 3D, 4D, 5D, etc. If you have multiple dimensions, directions, then the motion in one direction should not affect all the other motions in the other directions. So this is why we treat both the x and the y motions separately in our calculations. And we're going to see examples of how this is physically true. So if you guys turn to your packets and 2D kinematics on page 3, independence of motion in two dimensions, you should see here this image right in front of you. Here, this figure shows the trajectories of two softballs. One was dropped, the one on the left, and then the other one on the right was given an initial horizontal velocity of 2.0 meters per second. So imagine you're throwing that ball horizontally with a speed of 2 meters per second. This is what its trajectory would look like. So, I want you guys to pay attention here to the two paths. What is similar about them? So let's see here. I want to direct your attention to how these balls line up in the vertical direction. So as they fall down vertically, what do you notice here? They line up. Each second the strobe light flashes a picture. And after each of those seconds, each of those images, both softballs line up vertically. The vertical distance they fall is the same per second. What does that mean? We can probably predict that both softballs will fall the same vertical distance at the same time, regardless of what's happening here being thrown horizontally. Both balls will fall that same vertical distance and reach the floor at the same time. If you also remember back to our ticker tape skills, then you could also notice that the distance here, the space between the balls at each second, starts off small and then it starts to space out with each second. What does that show? Acceleration. So we're seeing here an acceleration downwards in the vertical direction. How does that look familiar? Gravity, guys. Now this next image shows the velocity components of the horizontally launched ball. So if you look at that ball on the right where it's thrown horizontally, this image here shows its vertical and horizontal components. So let's label these things here. Okay, so this one here is the y, oops, my mistake. That's the x. The x horizontal component, and this here is the y vertical component on the left. On the right side, part B, on image B, this shows both the x and the y components, as well as the resultant velocity when you combine both of these together. When you combine both components together, you should get this overall resultant velocity. You notice here that resultant and its two components line up with that resultant in that dashed line. Okay. So, I want you guys to pay attention here to the arrows, the vector arrows in the horizontal direction. What do you notice about the length of these arrows as time goes? They stay the same. If the length of these vector arrows stay the same throughout, that means the velocity in the x direction stays constant. And if we have a constant velocity, that means our acceleration in the x direction is 0. You see right there. Now how about in the y direction? You see it starts out small and then it starts to increase in length as you progress downwards. What does that show? We're seeing an increase in length, increase in speed. What does that show? Acceleration. So we accelerate from the top and going downward we start to see the acceleration. So that is why we have an acceleration in the y direction. This acceleration in the y direction pointing downward. Now I'm pretty sure you guys could take a guess as to what value that acceleration in the y is. Since it's an acceleration due to gravity, what is that going to be? 9.8 meters per second squared. Okay. Now if we look at the right side with the resultant velocity, does that resultant velocity start to increase in length? Does it start to accelerate over time? Well, we can see here. It starts off small and then over here at the last bottom here, it looks longer than it was initially. So we can say and also conclude that the resultant velocity as time passes also increases. If the x stays constant over time and if the y increases over time, then overall the resultant should also increase over time. Okay. So here's a checkpoint question for all of you to check your understanding. Does motion in the y direction affect motion in the x direction? If you guys say no, then you're correct. The answer is no. Back to that idea we saw initially, whatever motion happens in one direction should not affect the motion in the other direction. So we're going to do a little analysis here. Let's draw the free body diagram of each ball after they were launched. That means while they're suspended in midair. So why are we bringing forces into this? Well, as we learned before, forces is the reason behind motion. So we're going to see how the forces affect this 2D motion. Okay, here, so let's draw a box. Oh, no, that's an arrow. Yeah, let's just draw a plain old box here. Okay, so this is going to be object A and this is going to be object B. So if we look back to the example of the two softballs, the image with the two softballs, one is dropped and the other one is thrown horizontally. Let's treat the dropped one as A and the B as the one that's thrown horizontally. So let's label that. Let's be more specific. A as dropped and B as thrown. Okay. So let's start here. What force is always at play? There's always gravity. And where is gravity directed? Downward. Okay. Do we have any other forces acting upwards? Do we have a force that's acting upwards opposite gravity? Some of you might say there is a normal force, but let's see here. A normal force only happens when there's a surface. Are these objects acting on a surface? No, they're suspended in midair, so there is no normal force here to counteract the gravity. So it's just gravity happening here in the vertical direction. Now how about in the horizontal direction? Is there any force happening here in this horizontal direction? Well, what do you guys say? There should not be any force here in the horizontal direction. Why is it? We usually assume there's no friction or air resistance, which would typically happen in any direction. But in our analysis case, we assume there's no friction or air resistance here. So overall, it's just gravity acting in the downward direction on both objects. So how does this affect the acceleration here? Well, if gravity is the only force acting downwards, that is why, that is why our acceleration in the y is 9.8. What is 9.8? That is the acceleration due to gravity. Since gravity is the only force happening here, the acceleration of both objects in the y direction is 9.8 meters per second. Now, how about in the x direction? Since there's no forces here, since we have no net force here in the x direction, what does that say about the acceleration? That means it's also 0. So that is why our acceleration in the x direction is 0 meters per second. Because the only force that's happening here, is gravity. Hence why we have an acceleration here of 9.8 meters per second squared. Now I'm bringing back this image to further emphasize the point that acceleration in the x direction is 0, therefore our velocity in the x direction remains constant. Because we don't have any forces here, we don't have any forces happening in this horizontal direction, our velocity in the x direction can stay constant. Whereas since gravity is the only force happening in the y direction, that's why we see an acceleration here in the vertical direction going downward, and why the acceleration in the y direction is 9.8 meters per second squared. So to check your understanding, why do we say that our acceleration in the x direction is 0 and our acceleration in the y direction is 9.8? Well, if you guys refer back to the free body diagrams, then this free body diagram can explain why both accelerations are why they are. Because gravity is the only force acting downward, our acceleration is 9.8 meters per second squared, and since we don't have any forces happening in the x direction, the horizontal direction, we have no net force, therefore no acceleration. So now we go back to our original question. When you throw both objects horizontally with different speeds at the same time, which will hit the ground first? If you say both of them, then you're correct. It's both. If you think back to the image with the two softballs where one is dropped and one is thrown horizontally, both should hit the ground at the same time. This illustrates the point that whatever motion happens in one direction should not affect the other direction. So what happens in the x, regardless of how fast you throw an object in the x direction, it should not affect the time it takes to fall that y distance, that y vertical distance. So they should both hit the ground at the same time. Okay, so stay tuned. We're going to go see how we can apply these concepts to solving these 2D motion problems.